Welcome! Today, we'll tackle an interesting and fun problem called Goat Latin. This problem challenges us to manipulate strings in a creative way, testing our understanding of string operations and loops. Let's dive in and explore the solution step by step. In this problem, we are given a sentence as a string S, where the sentence consists of words separated by spaces. Each word is made up of English letters, which can be in lowercase or uppercase. Our task is to transform this sentence into something called Goat Latin and return the resulting string. To do this, we follow three specific rules. First, if a word starts with a vowel, whether lowercase or uppercase, we append ma to the end of the word. For example, the word apple becomes a plema. Second, if a word starts with a consonant, we remove the first letter of the word, move it to the end, and then append ma. For instance, the word goat becomes otma. Lastly, we add one letter to the end of each word based on its position in the sentence. This means the first word gets one a, the second word gets two a's, the third gets three, and so on. Once all words are transformed, we join them with a single space to form the final sentence. The output for this problem is a single string that represents the sentence transformed into Goat Latin. Let's look at an example to understand this better. Suppose the input string is I speak Goat Latin. The output for this would be ima pixmea otma atmomaya. Here's why: the first word, I, starts with a vowel, so we append ma and add one a for its position, giving us ima. The second word, speak, starts with a consonant. We move the s to the end, append ma, and add two a's, resulting in pixmea. Next, the third word, goat, also begins with a consonant. We take the first letter G, move it to the end, append ma, and then add three a's for its position, which gives us otma. Finally, the fourth word, Latin, also starts with a consonant. We move the L to the end, append ma, and add four a's, resulting in atmomaya. When we combine these transformed words with spaces, we get the final output, ima pixmea otma atmomaya. Now let's take a look at another example to reinforce the concept. If the input is the quick brown fox, the output would be hitma wikma round maya ox maya. Here's how it works: the first word, the, starts with a consonant, so we move the t to the end, append ma, and add one a, giving us hitma. The second word, quick, also starts with a consonant. We move the q to the end, append ma, and add two a's, resulting in wikma. Continuing, the third word, brown, starts with a consonant. We move the b to the end, append ma, and add three a's, giving ramaya. The fourth word, fox, also starts with a consonant. We move the f to the end, append ma, and add four a's, resulting in oxmaya. Combining these words with spaces gives us the output, hitma wikma round maya oxmaya. There are also some edge cases to consider. For example, if the input consists of a single word like apple, which starts with a vowel, the output is simply a plema. If all words in the input start with vowels, such as apple, orange, egg, the output becomes a plema orange mea egma. On the other hand, if all words start with consonants, for example cat, bat, rat, the output would be atma atma atramaya. These rules ensure that we can handle any valid input string and generate the correct Goat Latin transformation. To tackle the Goat Latin problem, we first considered a brute force approach. The intuition here is straightforward: process each word in the sentence one by one, applying the transformation rules directly. To start, we split the input string into a list of words. Then, for each word, we check if it begins with a vowel, like a, e, I, o, or u, and handle it accordingly. If it starts with a vowel, we simply add ma to the end of the word. If it starts with a consonant, we move the first letter to the end and then append ma. Additionally, we append a specific number of characters to each word based on its position in the sentence. For example, the first word gets one a, the second word gets two a's, and so on. Once all the transformations are done, we join the modified words back together to form the final Goat Latin sentence. While this approach is easy to follow and implement, it has a time complexity of n*m, where n is the number of words and m is the average length of each word. This is because operations like string concatenation and appending are performed repeatedly for every word. Now, while the brute force method is simple, it does have some inefficiencies.
For example, repeatedly checking for vowels and performing string concatenations can introduce redundant operations that could be optimized. This brings us to the optimized string manipulation approach. Instead of performing multiple appends and concatenations, we can streamline the process to make it more efficient. First, we use a set to store the vowels, which allows us to check if a letter is a vowel in one time. Then, as we iterate through the words using Python's enumerate function, we apply the transformations in a single pass. If a word starts with a vowel, we append ma. If it starts with a consonant, we slice the first letter, move it to the end, and then append ma. Finally, we add the appropriate number of characters by multiplying the character A with the word's index plus 1. Instead of modifying strings directly, which can be costly, we accumulate the transformed words in a list and join them at the end to produce the final result. This approach retains the same O and *m complexity but reduces the constant factors, making it faster in practice. The optimized string manipulation approach offers several advantages over the brute force method. By reducing redundant string concatenations, it becomes slightly more efficient and better suited for handling larger inputs. However, it does require more careful implementation, particularly when working with string slicing and indexing to ensure that transformations are applied correctly. This approach was ultimately chosen because it strikes a good balance between simplicity and performance. One key insight here is that Python strings are immutable, meaning that every time we modify a string, a new one is created in memory. This can quickly become expensive if done repeatedly. By using a list to accumulate results and joining the strings only once at the end, we minimize this overhead. Additionally, using a set for vowel checks ensures membership testing, which is faster than alternatives like lists. Multiplying a characters based on the index of the word is also an efficient way to handle the positional requirement without introducing unnecessary complexity. Although both the brute force and optimized methods share the same theoretical time complexity, the optimized approach is more scalable due to its reduced overhead. It avoids the inefficiencies of redundant string operations, making it better suited for larger datasets. However, it does require slightly more attention to detail when implementing steps like slicing and appending. Other alternatives were considered but ultimately rejected. For instance, using regular expressions to check for vowels and consonants would have added unnecessary complexity and hurt readability. Similarly, approaches involving stacks or deques were deemed excessive for such a straightforward transformation problem. In the end, the optimized string manipulation strategy stood out as the best choice. It balances performance, simplicity, and readability, making it a practical and clean solution to the Goat Latin problem. In this problem, we need to transform a given sentence into what is called Goat Latin by following specific rules. First, if a word begins with a vowel like a, e, I, o, or u, we append ma to the end of the word. However, if the word starts with a consonant, we move the first letter to the end of the word and then append ma. Additionally, for each word, we append the letter A repeated as many times as the word's position in the sentence, where positions start from 1. Importantly, the original order of the words in the sentence must remain intact. To address this systematically, we begin by parsing the input sentence. By splitting the sentence into individual words using Python's split function, we can isolate each word while keeping their order. For instance, given the sentence I speak Goat Latin, splitting it results in the list I speak Goat Latin. Next, we initialize an empty list to store the transformed words. This result list provides a structured way to accumulate the transformed words efficiently while maintaining their sequence in the sentence. Now that we have a list of words and an empty result list, the next step is to iterate over the words along with their positions in the sentence. Using a loop, we process each word while keeping track of its one-based index, which will later help us determine how many characters to append. In Python, we can achieve this with the enumerate function, starting the index at 1. For example, iterating over the list, I speak Goat Latin, would give us the word I with position 1, speak with position 2, and so on. Once we have the word and its position, we check the first letter of the word to determine if it is a vowel. A set of vowels makes this check efficient, as sets provide constant time membership lookups. If the first letter is a vowel, we append ma to the word directly. If it's a consonant, we remove the first letter, move it to the end of the word, and then append ma.
This distinction ensures we apply the correct transformation based on the word's starting letter. After transforming the word by either appending ma or rearranging its first letter, the next step is to append a characters based on the word's position in the sentence. For instance, if the word is in position 3, we append 3 characters to the end of the transformed word. This can be implemented efficiently using Python's string multiplication, such as a*I, where I is the position. Once the transformation is complete, we add the fully transformed word to the result list. Adding words to the result list ensures that we preserve the order of the original sentence while building the transformed output incrementally. Finally, after processing all words, we combine the transformed words into a single string. This is done by joining the words in the result list with spaces to form the final Goat Latin sentence. For example, if the result list contains ima, speakma, goatma, Latin mea, joining them produces the string ima speakma goatma Latin mea. There are several key insights to note about this algorithm. First, Python strings are immutable, which means creating new transformed versions of words is computationally efficient for this task. Using a list to store intermediate results is another important choice, as lists maintain the order of words, which is crucial for preserving the original sentence structure. For checking vowels, a set is ideal because it offers average O(1) time complexity for membership checks, making the algorithm faster. Lastly, joining the words into a final string at the end minimizes the overhead associated with concatenating strings repeatedly in the loop. From a data structure perspective, the list is used to hold the split words and the transformed words, as it provides efficient appending and maintains order. The set is used for vowels because its constant time lookups are well suited for frequent membership checks. When we analyze the time complexity of this algorithm, we see that splitting the sentence into words takes O(n), where n is the number of characters in the input. Iterating through the words involves k*m, where k is the number of words and m is the average length of a word, as we process each character in the words for transformations. Joining the transformed words into the final string also takes O(n). Therefore, the overall time complexity is O(n). For space complexity, the result list requires k*m, as it holds all transformed words, and the vowel set takes O(1) space because its size is constant. This gives an overall space complexity of k*m. Together, these complexities indicate that the algorithm is efficient even for longer sentences with many words. Here, we define a Python class called solution with a method named toGoatLatin that takes a sentence as input. First, we create a set of vowels, including both uppercase and lowercase, for quick lookup. Then, we split the input sentence into individual words using the split method, which gives us a list of words to process. To store the transformed words, we initialize an empty list called result. The next step involves iterating through each word in the list, along with its one-based index, using the enumerate function. For every word, we check if its first character is a vowel. If it is, we follow Rule 1 by adding ma to the end of the word. Otherwise, for words that start with a consonant, we apply Rule 2 by moving the first letter to the end and then appending ma. Finally, Rule 3 requires us to append the letter a repeated I times, where I is the current one-based index of the word. The transformed word is then added to the result list. Once all the words have been processed and stored in the result list, we combine them back into a single string using the join method. This joins all the transformed words with a space in between, forming the final Goat Latin sentence. The completed sentence is then returned as the output of the method. This approach ensures that all the rules of Goat Latin are applied systematically to each word in the input sentence. Here, we begin by importing the necessary libraries and defining the solution class with the toGoatLatin method. The first step is to prepare a set of vowels, both uppercase and lowercase, for quick lookup. This allows us to easily check if a word starts with a vowel later. Next, we split the input sentence into an array of words using the split method. This helps us process each word individually. To build the resulting Goat Latin sentence, we initialize a string builder called result. This is more efficient than repeatedly concatenating strings. Then, we loop through each word in the array using its index. Inside the loop, we extract the current word and create another string builder called goatWord to construct the Goat Latin version of that word. The first transformation checks whether the word starts with a vowel or a consonant. If the first character is a vowel, we simply append the word itself followed by ma as per the rules. If it starts with a consonant, we move the first character to the end of the word and then append ma. This logic handles the first two rules of the Goat Latin transformation. Now, we move to the third rule, which requires appending the letter a repeated, I+1, times, where I is the zero-based index of the word. To achieve this, we use a nested loop that iterates up to the word's one-based position, appending in it a goat word during each iteration. Once the word has been fully transformed, we add it to the result string builder. To ensure proper formatting, we also append a space after each word except for the last one in the sentence. This is managed by a simple condition that checks if the current word is not the last in the array. After processing all the words, the final Goat Latin sentence is stored in result. We return this as a string using the toString method. This implementation ensures that all three rules are applied correctly, and the resulting sentence is properly formatted as per the problem requirements. To solve this problem, we start with the input sentence, which is I speak Goat Latin. First, we define a set of vowels, including both uppercase and lowercase forms, to make it easy to check if a letter is a vowel. Next, we split the sentence into individual words, resulting in the list, I speak Goat Latin. We also initialize an empty list called result to store the transformed words. Now, we process each word one at a time. For the first word, I, we see that its first letter is a vowel. According to Rule 1, we add ma to the end of the word, which makes it ima. Then, per Rule 3, we append a once because this is the first word, resulting in ima. We add this transformed word to the result list, so it now contains ima. Moving to the second word, speak, the first letter S is a consonant. Applying Rule 2, we move the first letter to the end and add ma, giving us pixma. Then, Rule 3 tells us to append it twice since this is the second word, making it pixma. This is then added to the result list, which becomes ima, pixma. Next, we process the third word, goat. The first letter G is a consonant, so we apply Rule 2 by moving G to the end and adding ma, resulting in OGMA. Then, Rule 3 instructs us to append it 3 times, as this is the third word, forming okma. This transformed word is added to the result list, making it ima, pixma, okma. For the fourth word, Latin, the first letter L is also a consonant. By applying Rule 2, we move L to the end and append ma, which gives us ot and LMA. Rule 3 then specifies appending it 4 times, as this is the fourth word, resulting in otmalmaea. Adding this to the list, result now becomes ima, pixma, okma, otmalmaea. Finally, we join all the transformed words with spaces to form the output string, ima pixma okma otmalmaea. This is the final result for the first example. In the second example, the input sentence is the quick brown fox. First, we split this sentence into words, giving us the quick brown fox. We also initialize an empty list called result to store the transformed words. Starting with the first word, its first letter, T, is a consonant. Applying Rule 2, we move the T to the end, add ma, and append a once since this is the first word, resulting in heatma. This is added to the result list, which becomes heatma. For the second word, quick, the first letter, Q, is also a consonant. By Rule 2, we move Q to the end, append ma, and then add it twice as it is the second word, producing wikma. Adding this to the list, result becomes heatma, wikma. The third word, brown, starts with the consonant B. Following Rule 2, we move B to the end and add ma, which gives roundma. Then, Rule 3 directs us to append it 3 times because it is the third word, resulting in roundmaea. We add this to result, making it heatma, wikma, roundmaea. For the fourth word, fox, the first letter, F, is also a consonant. By Rule 2, we move F to the end, append ma, and then add it 4 times, since it is the fourth word, forming oxmaea. Adding this to the list, our result becomes heatma, wikma, roundmaea, oxmaea. Finally, we join these transformed words with spaces, producing the output string heatma, wikma, roundmaea, oxmaea. This is the final output for the second example. For the third example, the input is a single word, apple. We split this into a list containing just apple and initialize the result list as empty. Processing the first and only word, apple, we see that its first letter, is a vowel. By Rule 1, we add ma to the word, forming a plema. Since this is the first word, Rule 3 instructs us to append a once, resulting in a plema. Adding this transformed word to the result list gives us a plema. Since there is only one word, we simply join the words in result to produce the final output, a plema. To analyze the time complexity of the toGoatLatin function, we start by breaking down its operations into key steps. First, the input sentence is split into words using the split method. This operation requires n time, where n is the total number of characters in the input string, because each character needs to be scanned to identify word boundaries. Next, the function processes each word in the list of words. Let's represent the number of words as w. For each word, a few operations occur, checking if the first character is a vowel is an O1 operation due to the constant time lookup in the vowel set. Then, constructing the transformed word involves slicing or concatenating the string, which takes k time, where k is the word's length. Additionally, appending a repeatedly, based on the word's position, requires I time for the ith word. So, the total cost per word becomes k plus I. Summing this up for all w words, the transformations contribute approximately w asterisk k underscore bar, where k underscore bar is the average word length, and the repeated appending contributes w squared, as the sum of the first w integers is proportional to w squared. After processing the individual words, the next step is to join the transformed words into a single string using the join method. This operation takes total underscore chars time, where total underscore chars represents the total number of characters in the resulting transformed words. If the average length of each transformed word is m, this joining step contributes w asterisk m to the time complexity. Taking all these steps into account, the dominant term in the time complexity arises from appending a repeatedly to each word, as this contributes w squared. Therefore, the overall time complexity is w squared, where w is the total number of words. Now, turning to space complexity, the input string of length n requires n space for storage. Additionally, the list of words on the result list also occupy space. The words list contains w words, each of average length k underscore bar, contributing w asterisk k underscore bar. Similarly, the result list stores w transformed words, each with an average length of m, adding w asterisk m to the space complexity. Beyond input and intermediate storage, we must also consider auxiliary space. The vowel set used for constant time lookups occupies O1 space since its size is fixed, and temporary variables like word or goat underscore word require negligible space relative to the overall inputs. Combining all these factors, the dominant space usage arises from the result list, as it grows in proportion to the size of the transformed words. Thus, the overall space complexity is w asterisk m, where w is the number of words and m is the average length of each transformed word. Comparing this approach to a brute force method, manually iterating through characters to check vowels or constructing strings character by character would not change the asymptotic complexity but would introduce additional constant factor overhead. The current implementation optimizes these operations by leveraging a set for O1 vowel checks and efficient string manipulation techniques, such as slicing and concatenation, which operate in linear time for their respective inputs. Finally, let's consider the best, average, and worst-case scenarios for this problem. Regardless of the content of the input sentence, each word undergoes the same transformation steps, including vowel checks, string slicing, concatenation, and appending repeatedly. These operations do not vary based on the input, so there is no change in the computational cost across different cases. As a result, the time complexity remains w squared in all scenarios, and the space complexity stays at w asterisk m, where w is the number of words and m is the average length of the transformed words. This consistency across cases ensures predictable performance for the toGoatLatin function, making it both efficient and reliable for any valid input. When working on the GoatLatin problem, there are some common mistakes to watch out for. First, be cautious about string indexing and transformation. For example, if you forget to append ma or the correct number of a's, your output may only be partially transformed. Always double-check the final output format for each word to ensure it's accurate. Another frequent pitfall is overlooking edge cases. Scenarios like an empty string, a single word input, or sentences with extra spaces can lead to runtime errors or incorrect results. Be sure to test with edge cases such as an empty string or a single letter like a. Additionally, inefficient iteration is a concern, especially in languages like Python where strings are immutable.
Repeatedly appending to strings inside a loop can slow down performance.
Instead, collect transformed words in a list and join them at the end.
Also, pay attention to capitalization. If the problem specifies case-sensitive transformations, ensure that each word retains its original capitalization.
Lastly, be careful when checking the first character of a word for vowels. If you don't validate that the word is non-empty, you might encounter index errors. These tips can help you avoid common pitfalls and produce a robust solution.
Now, let's discuss some insights that are particularly valuable for interviews.
This problem is designed to assess your ability to process strings iteratively while applying specific transformation rules. Breaking the task into smaller steps, like splitting the string, transforming each word, and finally joining them back together, can simplify your implementation.
Efficiency is also a key focus.
For example, reducing string operations inside loops can make your solution faster. Using Python's join method or Java's string builder for concatenation is a great way to optimize performance. Edge cases remain critical here too. Be prepared to explain how your solution handles unusual inputs, such as empty strings or sentences with irregular spacing.
This demonstrates your attention to detail and testing thoroughness. Lastly, take advantage of language-specific features.
For example, Python starts with is excellent for checking vowels efficiently, and Java's charAt helps you access specific characters directly.
By leveraging these insights, you can craft a solution that is both efficient and resilient, and you'll be better equipped to discuss your approach during an interview.
This problem also shares similarities with several other string manipulation challenges that you might encounter. For instance, LeetCode 345, Reverse Vowels of a String, focuses on vowel manipulation and traversing strings, which is directly relevant to the vowel-based transformations in Goat Latin. Then, of course, there's LeetCode 824, Goat Latin itself, which is a direct implementation of these transformation rules. Another related problem is LeetCode 58, Length of Last Word, which emphasizes splitting strings and extracting specific components, a skill that's also handy in Goat Latin. Finally, LeetCode 151, Reverse Words in a String, involves splitting, reversing, and rejoining strings, which aligns closely with the iterative transformations you perform here.
Solving these related problems not only strengthens your understanding of string processing but also prepares you for variations you might encounter in technical interviews.
There are also alternative approaches you can explore to solve the Goat Latin problem. One option is to use a functional programming approach, such as Python's map function or list comprehensions, to apply transformations concisely. This can result in shorter, more elegant code, but it may be harder to read and debug for those new to the concept. Another method is character-by-character transformation, where you iterate through the string without splitting it into words. This avoids creating intermediate lists, making it more memory efficient, but it introduces complexity when handling word boundaries and transformations.
Lastly, you could use a regex-based approach to directly identify and transform words based on patterns.
While this method can simplify some aspects of the problem, especially for complex rules, it's often overkill for simpler tasks like Goat Latin. Each of these approaches comes with trade-offs, so it's important to choose one that balances clarity, efficiency, and maintainability based on the problem requirements.
Great job! We've successfully solved the Goat Latin problem and reviewed key takeaways. Remember, string manipulation is an essential skill in programming.
Keep practicing and exploring new challenges.
Thanks for tuning in, and I'll see you in the next session. That's the end of this tutorial.
I hope you found this explanation helpful for understanding the solution to this LeetCode problem.
If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions.
Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have.
Thanks for watching, and happy coding!